All right, in this example, we are going to look at graphing a function without actually being given the function. So we have known information. We have, in this first column, we have x values. We have x equals 2, x equals 4, and x equals 6, as well as some intervals. So the region where x is less than 4, the region where x is between 2 and 4, and the region where x is between 4 and 6, as well as greater than 6. So you notice in our second column, we know that when x equals 2, y equals 1. When x equals 4, y equals 4. And when x equals 6, y equals 6. And then we have information about both the first and the second derivatives. Now remember, if the first derivative is positive, that would indicate increasing. So f prime of x is some positive number. We know the graph is increasing. If f prime of x is a negative number, it is decreasing. And if f prime of x equals 0, that is a possible max or min. Also, what we know about the second derivative, f double prime or y double prime of x, if the second derivative is positive, it's going to be concave up. So either the left or the right half of a concave up. And if the second derivative is negative, we'll have concave down. So the left or the right half of some curve, which is concave down. And second derivative equal to 0, that may represent an inflection point where the concavity changes. So we change from concave up to concave down. All right, also the second derivative being positive or negative lets us know if something is a max or a min. So that's the second derivative test for extrema. All right, so let's think about graphing this. I'm going to erase this stuff I've written, and we're going to kind of start thinking about this piece by piece, maybe using a number line to help us graph. All right, so I'm going to go ahead and take this sort of number line I've drawn here. I'm going to divide it into pieces. It doesn't have to be perfect, but we have 2, 4, 6. And of course, on these intervals, there's negative infinity to 2, 2 to 4, 4 to 6, and 6 to infinity. So we want to think about what the behavior is. Unfortunately for us, all of these output points, oh my goodness, output points here, all of those output points are positive. You know, we can think about drawing our y-axis, but that really doesn't matter so much as actually the curvature. So we do know we have this point. I'm going to go ahead and plot over 2 up 1. There's some ordered pair, 2, 1. I also have over 4 up 4, so I'll just make that a little bit higher. Maybe even a little higher than that. We'll say we've got 4, 4. And that looks messy. And then we have over 6 up 7. So I'm going to make that point a little higher. And of course, this doesn't have to be exactly to scale. The whole idea here is we're trying to get an idea of what's going on. So first of all, if we think about x being less than 2, that's this region over here on the left of 2. We know that the first derivative is less than 0. That lets me know it is decreasing. And the second derivative is positive, so it's decreasing, and then positive second derivative, concave up. So concave up like a cup, only one half of this is decreasing, right? So that first half, that is decreasing concave up. So we are decreasing concave up from somewhere over there on the left to that point. Now, what is happening at that point, 2, 1? Well, y equals 0, so that might be a max or a min. That's a critical point. That first derivative is equal to 0. So critical point. And if the second derivative is positive, that lets me know it might be a min by the second derivative test for extreme values. So I'm going to put a little note there, positive min. So that would represent a minimum value. Now let's look at our next interval. So we'll say over here between 2 and 4. So the first derivative is greater than 0. So that's a positive first derivative. So we know it is increasing. And the second derivative is greater than 0. So again, that's concave up. Concave up increasing. That is the right half of our concave up. So we know our graph at this point is going to start turning and curving up. Now, of course, the way I've spaced this, my 4 point wasn't exactly right. So, again, it doesn't have to be perfect. It's just the idea of what we are doing. And we just want to make sure that we are drawing that graph as it should appear. So we go up. That is concave up. It's curving up. Now, what is happening here at 4, 4? The first derivative is positive. So that means, again, we know we are increasing. The second derivative is equal to 0. So that represents an inflection or possibly change in concavity at that point. Gotta write the correct word. So it's a change in concavity. So I might expect concave down to occur next. I can't be certain. Let's continue moving along within our problem here. So on the interval from 4 to 6, first derivative is greater than 0, so it is still increasing. But now my second derivative is less than 0. So that is concave down. Concave down, increasing, is going to curve sort of like that. So I'm going to kind of change my point here. We've got 6, 7 was my point. And again, we've got that concavity right there. So it does hold, like we predicted, that at 4, 4, this was some sort of inflection. And so we have that concave down. All right, moving through at x equals 6, we have that point y equals 7, which could represent a max or a min because the first derivative is equal to 0. So that's a critical point. Since the second derivative, by the second derivative test for local extrema, since the second derivative is negative, we know that this point is representing a maximum. All right, so last piece here. Pick another color we haven't used. X greater than 6. So for all x values that are to the right of 6, we notice the first derivative is less than 0. That lets me know this is going to be decreasing. And the second derivative is less than 0. So concave down. Concave down, decreasing. The graph is going to move sort of like that. So if I were to try and sketch this, and I'm going to just sketch this here, what we see is that this graph is doing something like this. We have a minimum at 2, 1. We have the inflection where the concavity changes at 4, 4. And then a maximum at the ordered pair 6, 7. And that's just the general idea for how we would solve or sketch the graph of this problem. We would have something that looks like this on our paper. We know the points, we know the curvature, we know where the max and the min and the inflection point are. And of course, you're going to see a problem like this potentially on your lab that may have many more maxes and mins and increasing and decreasing, and you need to be able to interpret that all together. So I think this is a very good conceptual example that lets you see how just knowing the facts about the first derivative and the second derivative allows us to get a good idea, good understanding of the shape of the curve. So I hope that helps, and please let me know if you do have any questions. I'm here to be of assistance. Have a great day.